Welcome to American Wood Council's live learning event. Our lawyers make us say this, but this webinar is designed to provide general information and does not constitute professional or engineering advice. This webinar is being recorded. By continuing to stay on the webinar, you consent to being recorded. Please note, today's session is registered with the American Institute of Architects and the International Code Council. Credits will be automatically reported to the AIA for anyone who has provided their AIA member number at registration. Now we would like to welcome you to our course, Fire Design Specifications for Wood Construction. This presentation is worth 1 LUHSW with the AIA and 0.1 credit with the ICC. To receive credit for the course, you must attend this webinar for a minimum of 50 minutes. At the end of 50 minutes, you will see your certificate appear on your console. Your certificate will also be in your learner profile within 1 day on learn.awc.org. At the end of today's session, our presenter will have a live Q&A with the audience. Please input your questions into the Q&A panel throughout the session. And without further delay, I present to you our presenter, Jason Smart, Director of Fire Engineering with the American Wood Council.
All right, welcome to everyone here in our audience, and thank you for having me. It's an honor to have this opportunity to present to you today. As was mentioned, I am Jason Smart, Director of Fire Engineering at the American Wood Council. And today I'm going to cover the fire resistance design of mass timber and fire protection of connections associated with tall mass timber construction types, specifically using primarily the Fire Design Specification, the AWC FDS, for that purpose. Please note that this webinar and associated slides provide pertinent information regarding the design of wood structures, but they should not be used as a substitute for competent engineering support and expertise. Here's the basic course description for today. I think you've all seen this description already with the materials that you received previously when you registered for this course, so we'll just skip straight to the learning objectives now. The learning objectives for this course are listed here. We'll take a quick look at building code requirements relating to the fire safety of mass timber construction. I'll also introduce the code reference standards and other design guidance that can be used to demonstrate compliance with fire safety requirements. Then we'll explore what's in these design standards and learn a little bit about how to use the standards in design of mass timber structures. And the fourth objective for today is to delve into a few of the ways in which these provisions can be used in the fire design of protection for connections. Just to give a brief overview of what we're going to cover here, I've broken this presentation into 4 sections. Each of these sections relates to one specific learning objective one of the objectives that I just listed. So in the first section, I'll give a brief overview of the building code provisions related to fire safety of mass timber construction. Then we'll talk about the standards and design resources that are available for mass timber design in order to demonstrate compliance with the code provisions. In the third section, we'll delve into the contents of these standards and explain how they can be used for fire design of mass timber buildings. And then to wrap up our presentation, I'll go through some design examples for fire protection between fire resistance rated wood members. Fire protection of connections, that is, between fire resistance rated wood members. So let's start with the foundation of understanding the fire safety related code requirements that apply to the new mass timber construction types that are in the IBC. Specifically, by those new mass timber construction types, I mean types 4A, 4B, and 4C construction. In addition to code provisions relating to fire resistance, I'll briefly mention some of the other fire safety related code provisions as well here. I'll get us started with a high-level overview of the fire safety related building code provisions that are applicable to mass timber construction. Many of these code provisions rely on AWC standards like the NDS and the FDS, and design guidance in TR10 as well, Technical Report 10. I'll talk more about the AWC standards in the next portion of our discussion, but the code provisions that I'm mentioning here are from the 2024 I-codes. They're also the same as the 2021 I-codes, at least the provisions that I'll be discussing here. The I-code family includes the 2024 International Building Code and the 2024 International Fire Code, which contain the provisions applicable to these new mass timber construction types. The reason I'm basing this on this presentation on the most recent I-codes instead of an earlier version is because the new mass timber construction types were newly introduced in the 2021 edition of the I-code family. So earlier code editions recognized heavy timber construction, which was previously known as type 4. It was just type 4 because that was before the other type 4 construction types were introduced. But these earlier I-code editions did not include the 3 new mass timber construction types that we'll be talking about here. So these, as I mentioned, these 3 new mass timber construction types are types 4A, 4B, and 4C construction. In these new mass timber construction types, all of the building elements must be either mass timber or non-combustible materials. Several of the key fire performance features that have been built into these new provisions for types 4A through 4C construction are listed here on this slide. For example, as I just mentioned, all of the building elements need to be either mass timber or non-combustible materials. Also, the new mass timber provisions require that mass timber elements need to be protected with non-combustible protection. That's a new defined term, as specified in section 602.4 of the IBC. For most mass timber surfaces in type 4B and all mass timber surfaces in type 4A, the requirement is that 2/3 of that fire resistance needs to come from the non-combustible protection. Structural elements are required to have a fire resistance rating as shown in IBC Table 601 and also in IBC Table 705.5, whichever is greater. The adhesives used in CLT are required to be qualified through a series of both small-scale and large-scale fire tests. This is to ensure that they don't undergo heat delamination, which could lead to fire regrowth. No combustibles are allowed in concealed spaces except for those materials which are currently allowed in plenums by the International Mechanical Code. So an example of that would be insulated wires. Not a whole lot of fuel load there. In types 4A and 4B construction, one of the other requirements is that mass timber floors are required to have a minimum 1 inch thick non-combustible material above the mass timber. That's on the floors. In all 3 of the new construction types, everything outboard of the mass timber and the exterior walls is required to be non-combustible. That is, except for the water-resistant barrier, which is required, or that's also required to meet certain fire performance thresholds. Also, exterior mass timber walls are required to have at least 40 minutes worth of non-combustible protection on the outside. There are also requirements for non-combustible protection to be applied during construction and for water supply to be present, and standpipes need to be installed as well. The requirement for non-combustible protection during construction applies to mass timber surfaces that are more than 4 stories below the uppermost floor under construction. One thing I want to stress is that for all 3 of these new mass timber construction types, automatic sprinkler systems compliant with NFPA 13 are required. And in buildings greater than 120 feet tall, redundant water supplies are also required. These provide an added level of safety that would normally only be required for buildings that are greater than 420 feet. But these are, of course, are applied to buildings greater than 120. Also, shafts are required to be constructed of non-combustible materials in buildings over 12 stories or 180 feet. There are also additional requirements beyond the ones I've listed here. But of all the fire safety requirements we just went through, the one that's most pertinent for the rest of our discussion in today's presentation is the requirement for structural elements to have specified fire resistance ratings in accordance with IBC Tables 601 and 705.5. In the building code, the required fire resistance of a given building element depends primarily on the type of construction. And in the case of exterior walls, the required fire resistance rating also depends on occupancy group and fire separation distance, in addition to construction type. Table 601 of the IBC indicates the required fire resistance rating based on construction type. And as you can see in the column headings across the top of the table, as shown in this representation of IBC Table 601, it applies to all construction types, types 1 through 5. The three new construction types for mass timber are circled here in red, so you can distinguish them easily from the other columns which pertain to all of the previously existing construction types. Here's one of the big differences between traditional heavy timber construction, now called Type 4HT, versus the three new mass timber construction types. The new mass timber construction types require fire resistance ratings for building elements like the primary structural frame, floors, and roofs. Conversely, in traditional Type 4HT, there is no specific fire resistance rating requirement. Rather, Type 4HT building elements are required to meet the minimum cross-sectional dimensions specified in Table 2304.11. Notice here that the fire resistance rating requirements for new Type 4A are the same as those for Type 1A, which is the construction type that allows for unlimited heights and areas for most occupancies. This amounts to a 3-hour fire resistance rating requirement for the primary structural frame and for bearing walls, both interior and exterior. And there's a 2-hour fire resistance rating requirement for floor construction and associated secondary structural members. Likewise, both 4B and 4C have the same fire resistance rating requirements as Type 1B. Here we have 2-hour fire resistance rating requirements for nearly every building element except for the roof, which requires a 1-hour rating and non-bearing walls. Now, despite these equivalencies to Type 1 construction in terms of required fire resistance ratings, the limits on heights and areas for Types 4A, 4B, and 4C are not unlimited. They're significantly more strict overall, which adds one of the many layers of conservativeness to the code provisions for mass timber. The code recognizes 7 methods for establishing fire resistance. Any of these 7 methods can be applied to any construction type wherever the fire resistance ratings are required. They are all based on the same standardized fire exposure, and that's as specified in ASTM E119. Of the 7 recognized methods for determining a fire resistance rating, the one I have listed in red on this slide is the one we're primarily talking about today. Specifically, I'm referring to the calculation methods described in section 722. All right, well, we just took a brief look at the fire safety related code provisions for mass timber construction, especially those relating to fire resistance rating requirements. Now let's review the code reference standards and other design guidance available for the purpose of demonstrating compliance with these code requirements. We'll talk about available resources, how they're referenced in the code, and what types of guidance they provide. IBC section 722.1, which I just mentioned as one of the compliance pathways for demonstrating fire resistance ratings, references chapter 16 of the National Design Specification for wood construction. That's specifically for the purpose of calculating fire resistance ratings of exposed wood members and decking. AWC's Technical Report 10, or TR10, provides background, empirical validation, and examples on how to perform the calculations specified within Chapter 16 of the NDS. So TR10 serves as somewhat of a secondary reference in the code. TR10 and Chapter 16 of the NDS deal with the same methodology. It's a mechanics-based methodology, which I'm going to describe in more detail shortly. In fact, Chapter 16 of the NDS is based on the methodology presented in TR10. However, TR10 goes into a lot more detail and gives significantly more guidance than the NDS, so it's a great resource for designers who want to fully understand the provisions of the NDS and show compliance with them. More recently, the AWC Fire Design Specification, FDS, has been developed to provide a lot more guidance on fire design of wood members and assemblies, including guidance for mass timber. And as indicated by the title of this webinar, that's what I'll be focusing primarily on for the rest of our presentation today, the AWC Fire Design Specification and how it can be used for designing mass timber. Fire design of mass timber, that is. Here's the actual code language from IBC section 722.1, which deals with calculated fire resistance. As you can see in the highlighted text, Chapter 16 of the NDS is referenced as the standard for calculating the fire resistance of exposed wood members and decking. Chapter 16 of the NDS allows the fire design of exposed wood members for fire resistance ratings up to 2 hours. So the limit is 2 hours for exposed wood members. We'll talk about protected wood members also in a little bit. Chapter 16 also applies to any exposed wood member, including those in beams, columns, wall assemblies, floor ceiling assemblies, and roof ceiling assemblies. Materials addressed within Chapter 16 of the NDS include sawn lumber and glued laminated timber, or glulam. But then also the NDS was expanded in 2015 to address fire design of structural composite lumber, or SCL, and cross-laminated timber, CLT. And then more detailed provisions using the same mechanics-based model are provided in Chapter 3 of the AWC Fire Design Specification. Like the NDS, the FDS can be used for calculating the fire resistance of exposed wood structural members. But the FDS provides far more guidance than the NDS. For example, the FDS has provisions for calculating the fire resistance of protected wood members, fire resistance rated assemblies, and connections that can be designed using the NDS, or protection of those connections, that is. Some of the guidance provided in the FDS that is not included in NDS Chapter 16 include the following. In Section 3.2 of the FDS, there are calculation procedures provided for determining the char rate and char depth of exposed wood members. These provisions are consistent with NDS Chapter 16 provisions, but the FDS goes further. For example, the FDS provides, or it implements new procedures to account for char penetration at intersections and abutting edges of exposed wood members. And then using the char depths calculated in accordance with Section 3.2, Section 3.3 of the FDS provides calculation procedures for determining the structural fire resistance of those exposed wood members. As with Section 3.2, these provisions are consistent with, but more extensive than NDS Chapter 16 provisions. Once the reduced section properties of the wood members are calculated, using the provisions of FDS sections 3.2 and 3.3. The design strength used to determine the fire resistance is calculated by multiplying reference design values such as bending strength and tensile strength by the adjustment factors specified in Table 3.3.2, which you can see here. The K factors are applied to adjust the respective design values to an average strength level. As you can see, these factors range from 1.67 for bearing strength to 2.85 for bending and tensile strength. Section 3.4 of the FDS contains new provisions for determining the protection time provided by multiple forms of protection. Recognized forms of protection include additional wood cover, Type X gypsum panel products, specified types of insulation, and various combinations of these. The methodology and empirical basis for these provisions are the same as those that were used to justify the non-combustible protection provisions required for types 4A, 4B, and 4C construction in the IBC. Section 3.5 of the FDS contains new provisions for calculating the structural fire resistant time of protected wood members and assemblies. Again, these provisions are consistent with code-recognized procedures for protection of mass timber elements. Note that the FDS provides guidance for design of both combustible and non-combustible protection. An example of combustible protection would be additional wood cover added to the protected wood member, whereas an example of non-combustible protection would be gypsum board applied to the protected wood member. These provisions for design of fire protection, both combustible and non-combustible protection, allow for designs that go beyond the 2-hour fire resistance rating limit that I mentioned a few minutes ago, which applies to the exposed wood member itself. Section 3.6 of the FDS includes new provisions for calculating the thermal separation time provided by an assembly of wood layers, and also provided by Type X gypsum panel products, insulation, or some combination of these types of thermal separation protection. Note that the concept of thermal separation is a different one from that of the concept of protection time, which I mentioned a couple slides back. Although the same materials can be used for both thermal separation and fire protection, the calculation procedures are different. Both of these concepts play specific roles in fire design of wood members, and in design of connection protection, and in design of assemblies. We'll get into that in a little more detail in the next section of today's webinar. Section 3.7 of the FDS clarifies that burn-through detailing is only required where thermal separation is required. This section then references other sections within FDS section 3.6 for the purpose of thermal separation time calculations. And importantly, Section 3.10 of the FDS provides specific requirements for design of fire protection of connections. We're going to revisit these FDS provisions from FDS section 3.10 in the last segment of our presentation today, which deals exclusively with the topic of connection fire protection. So in this next section, let's delve into ways in which compliance with the building code provisions can be demonstrated through fire design using the standards and design guidance that we just looked at, and primarily using the fire design specification. All right, here's FDS table 3.3.1.2 again, and it provides a quick design reference for determining the char depth at a given exposure time. Those are the values you see in the middle column. The char depths are given in inches for corresponding fire resistance times of 1 hour, 1.5 hours, and 2 hours. The column on the right provides values of effective char depth, or A sub EFF. Notice that these values are about 20% greater than the values in the middle column. This additional 20% increase in the assumed char depth provides a further reduction in section properties to account for strength loss in the heated zone, and also a little bit to account for rounding at corners. But primarily that 20% increase in char depth, effective char depth, accounts for strength loss in the heated zone. So the fire design of exposed wood members is based on effective char depth rather than A sub char or char depth. But there are also some design applications that use the values in the middle column as well, the char depth values. And we'll talk about those a little bit later when we talk about connection protection. The table I showed on the last slide provided char depths and effective char depths for wood products other than CLT. Now let's talk about the char depth model specified in the FDS for CLT, which is different from the model used for other wood members. The CLT model was developed to more accurately fit the empirical char depth data for CLT, as opposed to the model used for other wood products. As you can see from this scatter plot, the model fits the empirical data fairly well. That said, I also wanted to briefly note that work is currently underway to validate and refine a possible alternative char depth model for CLT, and it would assume the same char depth as for other wood members, except at the locations of edge joints between laminations. And at those locations of edge joints between laminations, char penetration would be assumed to advance at a rate that's faster than that which results from A sub char. But going back to the provisions in the FDS, here are the char depth values resulting from the CLT char depth model. This table, which also comes from FDS section 3.3, provides effective char depths for CLT with various lamination thicknesses. The table applies only to CLT in which all of the laminations in the layup are of equal thickness. But then the FDS commentary also has provisions for fire design of CLT with laminations of unequal thicknesses throughout the thickness through the layup. Notice that the effective char depth values in this table are generally greater than the values in the NDS table I showed previously for other wood members, or that is the FDS table that I showed for other wood members. This is not because CLT has different nominal char rates. In fact, it's assigned the same nominal char rate as for other wood member types, and that's usually taken as 1.5 inches per hour. But rather, the reason for this difference is because of the different char depth models that are used. And as I mentioned, CLT uses a separate model. Note also that CLT with thinner laminations has a greater effective char depth at a given fire resistance time. And this too is the result of the CLT char depth model. Using the CLT char depth model, a thickness of CLT equal to the effective char depth is subtracted from the exposed surface in a manner similar to the procedure used for design of other wood members. However, unlike other wood members, the cross-section of CLT has distinctive orthogonally oriented layers, and this needs to be accounted for in the mechanics-based fire design of CLT. For more details on how to perform this type of calculation, you can refer to TR10 example 4.6, because that provides an example of how to go through the mechanics-based design of CLT. But then there's also a simplified method for design of CLT that's also recognized, and that's what's outlined here on this slide. So, for example, the example shown on this slide assumes a 5-layer CLT having 1 3/8 inch thick laminations, and in this case, the fire design could conservatively be based on the design properties for a 3-layer CLT made of the same lamination types and grades. That is, provided the remaining effective char depth is greater than or equal to the combined depth of the 3 laminations, which happens to be 4 1/8 inches in this case, in this example. So this simplified methodology would work conservatively for a 1-hour fire resistance rating in this example, but it would not work for a 1.5 or 2-hour fire resistance rating. The calculated fire resistance of timber decks, including nail laminated timber, can be calculated using section 3.2 or 3.3 of the FDS. And the provisions of section 3.3.3.1 apply to tongue and groove planks or mechanically laminated dimension lumber set on edge and nailed to the adjacent pieces. Under this method, char penetration between abutting laminations is assumed to extend into the decking a distance of 2 times the normal calculated char depth, or 2A char. The distance, or the increased char depth at abutting edges, creates a triangular shaped char depth profile at each lamination interface. The resulting section is then analyzed using the mechanics-based methodology. This design method for timber decks has been validated using existing fire resistance test data, and it allows for optimized design of timber decks because it yields higher and often more accurate calculated fire resistance ratings than the NDS procedure, and that's especially the case for thicker timber decks. There are also 2 exceptions to these provisions, which are similar to the lumber decking fire design provisions in the NDS. In the first exception, single and double tongue and groove decking are permitted to be designed as an assembly of wood beams fully exposed on one surface only. And of course, that's the surface facing towards the fire. In the second exception, butt-jointed decking is designed as an assembly of wood beams fully exposed on the bottom and then partially exposed on the sides of each lamination. To compute the effects of partial exposure on the sides of each lamination, the char rate for this exposure is taken as 33%, or 1/3 of the effective char rate. For butt-jointed timber decking, which includes NLT, these calculation procedures do not address thermal separation. However, the FDS provides other guidance on how to design for thermal separation. For example, thermal separation can be achieved by the addition of layers such as gypsum board on the ceiling or a wood structural panel subfloor on the top surface. A cast-in-place floor topping such as gypsum concrete would further enhance thermal separation. These added components also have benefits from an acoustic standpoint. Now, as for glued laminated timber beams, these members typically have stronger laminations at the top and bottom than when compared to laminations closer to the neutral axis within the layup. Because of this, additional tension laminations are required to replace interior core laminations so that the extreme fiber remaining on the reduced section will have adequate strength. This is a detailing provision that requires communication and coordination between those responsible for the fire resistance design and those responsible for the structural design. The Fire Design Specification contains provisions that, from a practical standpoint, give the same layups as those in the NDS, but they are greatly expanded for the purpose of clarification. These provisions are given in FDS section 3.3.3.2, and I'm only showing the charging language here, but there's a lot more information in this section, too much to fit on this slide actually. To illustrate these expanded and clarified provisions, the FDS provides diagrams of glued laminated member layups for various fire resistance ratings and exposure configurations. These are provided in FDS figures 3.2 and 3.3, a portion of which here is shown on this slide. This is from figure 3.2. So far, I've just been describing the fire resistance designs and calculations for exposed mass timber, and for the most part, these procedures are the same as those provided in the NDS. Using this mechanics-based method, the two main variables that determine the fire resistance of an exposed wood member are, firstly, the cross-sectional dimensions of the wood members, and that's why larger members tend to have greater fire resistance, and then secondly, the ratio of the actual design load on the member to the full ASD load. This latter variable is known as the load ratio. If the load ratio on the wood member is decreased to a ratio of less than 100% of allowable stress design, the result will be an increase in fire resistance. This is due to the fact that a smaller ratio would not require as large of a remaining section to continue supporting the load, thereby accommodating greater section loss and hence a longer exposure time. But remember that when it comes to the fire resistance requirements for the three new mass timber construction types, you can combine the calculated fire resistance of the wood member itself with the added fire resistance of any non-combustible protection that may be applied to the surface of it. This is a very important point because it's one of the characteristics that distinguishes fire design of wood from other construction materials. For wood, you can rely on a certain calculated amount of inherent fire resistance in the member itself, and then, if necessary, add to that any additional amount of protection that may be prescriptively required or necessary to achieve a particular fire resistance rating. As I mentioned earlier, FDS section 3.3 provides guidance on how to determine the amount of protection time provided by additional wood cover and wood membranes. Additional wood cover is protection from additional wood members that are added to the wood structural member being protected. The provisions for wood cover apply where additional wood protection is in direct contact with the protected member. This is represented by the blue line on this graph showing protection time as a function of wood cover depth. Conversely, The provisions for wood membranes apply where wood protection is not in direct contact with the protected member. This is shown as the orange line in this graph here. Notice that the protection time from a wood membrane that is not in contact with the protected member is generally less than the protection from wood cover that is in direct contact. An exception to this rule is for wood membranes that are about 1/2 inch or less, where the protection time is about equal regardless of whether or not it's in contact with the protected member. You can see that at the bottom end of this curve here. Table 3.4.2.1 of the FDS quantifies the protection time provided by varying thicknesses of Type X gypsum panels. These times are associated with specific attachment schedules of the gypsum as specified in the table. Each layer of 5/8 inch Type X gypsum provides 40 minutes of protection, while each layer of 1/2 inch Type X gypsum provides 30 minutes of protection. And FDS Table 3.4.3.1 quantifies protection times provided by various types and thicknesses of insulation when used within the fire resistance rated assembly. As with other protection time provisions, these values are also empirically derived through standard fire resistance tests. As you can see, the times associated with mineral wool bats in this table are significantly higher than those associated with fiberglass bat insulation. And this is owing to the fact that there is a difference in melting points between mineral wool insulation versus fiberglass insulation. But again, these are empirically derived values from actual ASTM E119 tests. I also want to mention that unlike protection time from wood and gypsum, the protection time associated with insulation is not cumulative, even when there are multiple layers of insulation used within the assembly. You can only claim the protection from one of the layers of insulation. Lastly, in this last section, let's talk about how to design fire protection for mass timber connections. As I mentioned previously, in the new types 4A, 4B, and 4C construction, fire resistance ratings are required for most of the structural elements. This is one of the things that makes these new mass timber construction types very different from traditional heavy timber construction, and it necessitates a totally different approach when it comes to connections as well. Wherever structural members or assemblies are required to be fire resistance rated, the code requires the connections between those members or assemblies to have an equal level of fire resistance. Unlike for timber members, which are recognized to have an inherent level of fire resistance on their own, connections are required to be protected. In other words, 100% of the required fire resistance for a connection must come from protection applied over the connection rather than from the connection itself. These are two excerpts from the code sections which require protection of connections between structural members of the primary structural frame. Specifically, these requirements are found in IBC sections 704.2 and 704.3. As you can see, the code requires such structural connections to be protected on all sides. You may recall from a previous slide showing an excerpt from IBC Table 601 that these primary structural framing members are required to have a 3-hour fire resistance rating in Type 4A construction and a 2-hour fire resistance rating in Types 4B and 4C construction. Here's an excerpt of the IBC provisions dealing with fire protection of connections in mass timber construction. And as you can see here, two options are provided. The first option is to perform a standard ASTM E119 fire test, in which the connection is included within the tested assembly. As with any standard fire resistance test of a load carrying assembly, the connection would need to be loaded during this test. And then the second option is an engineering and analysis option. The design objective in such an analysis is for the average temperature rise at the interface between the protection and the connection itself to be limited to 250 degrees Fahrenheit. Notice that the last sentence of item 2 clearly defines the connection as including the connection hardware, fasteners, and portions of the wood members included in the design of the connection. included in the structural design, that is. This is an important point because it means that the connected wood members themselves cannot be used as part of the protection unless those members are intentionally oversized for this purpose. So if they're oversized beyond what is necessary for the structural design, then you can rely on a certain portion of those wood members for protection. Otherwise, you cannot. And generally speaking, the connection protection is made up of distinct members of either wood, gypsum, or some other approved material that is applied over the connection. With regards to option 1, the testing option, this can be useful in certain circumstances, especially for unusual connection designs involving proprietary components or where a connection is part of a tested assembly, like a truss plate. But obviously it would be impractical to test every connection configuration. This is where the second option, the engineering analysis option, provides a more practical solution for everyday designs. The Fire Design Specification provides the guidance for performing such designs of fire protection for connections. And I'll talk about that in just a little bit in this last segment here, after we look at the applications or applicable provisions in the NDS. NDS section 16.3 states that connections between members which are required to be fire resistance rated must be protected from the fire exposure, thereby echoing AWC sections 704.2 and 704.3. This section also provides requirements for the manner in which connections are required to be protected. This protection can be provided by either additional wood cover beyond just the wood member in the connection itself, or beyond what's required for the structural design of that wood member, as I mentioned, or it can be provided by a fire-rated gypsum boards such as Type X gypsum, or other approved materials for which the required fire protection time is demonstrated. And of course, you're also allowed to use some combination of the three options that I just mentioned here. The three material types that I just mentioned, that is. And again, just like for member design, TR10 and the FDS both provide detailed guidance on how to design connection protection using these various materials. These documents explain how to design the connection protection in order to meet the code-specified design objectives associated with the engineering analysis option in the IBC. Specifically, I'm referring to the average temperature rise criterion of 250 degrees Fahrenheit. And by the way, I wanted to just point out that this is a temperature rise criterion, so it's when I say a criterion, a threshold of 250 degrees Fahrenheit, I'm referring to 250 degrees above ambient temperature. So that's not an absolute temperature. Furthermore, TR10 contains examples and details that graphically show how to properly design the protection for some of the more common connection configurations. The details on this slide are from TR10. The one on the left shows one possible method of protecting an angle ledger. That's a connection between a CLT floor and a supporting CLT wall that uses an angle. And the detail on the right shows a design example of protection from a beam column connection using a concealed knife bearing plate. As for the fire design specification, provisions for the protection of connections are contained in section 3.9. Depicted here are three examples of connections from wood members that could be required to have a fire resistance rating in the new mass timber construction types. These examples were all designed in accordance with FDS section 3.9 using wood cover to protect the connections. And the figures you see here show the idealized cross sections of the connected members at the end of the fire resistance rating time. Similar protection can be provided by gypsum panels, a combination of wood cover and gypsum panels, or other proprietary configurations. So let's look at a couple of examples on design of connection fire protection in accordance with the FDS. The FDS specifies that the thermal separation time provided by additional wood cover can be determined by multiplying the calculated protection time, or T sub P, by a factor of 0.85. For example, assuming a nominal char rate of 1.5 inches per hour, if a single layer of wood having a thickness of 3 inches is used to provide fire protection to a wood member, the protection time, or T sub P, provided by this layer would be calculated as shown in this equation here. In this example, it's 141 minutes. However, if this 3-inch thick layer of wood is used to protect a connection, then it must also provide thermal separation to limit the average temperature rise at the interface between the protection and the connection to 250 degrees or less. As noted above, the thermal separation time provided by this wood protection can be determined by multiplying the protection time by 0.85, and that would calculate then a thermal protection time of 120 minutes, or thermal separation time of 120 minutes. You can see that here. The FDS also provides an approach for determining the thermal separation time of gypsum board. Specifically, the thermal separation time of gypsum board is taken as the non-combustible protection time multiplied by a factor of 0.5. So a single layer of 5/8 inch Type X gypsum board, which has an assigned non-combustible protection time of 40 minutes, would be assumed to provide a thermal separation time of 20 minutes. In this detail, you can see that clearly the single layer of 5/8 inch Type X gypsum board on the ceiling would not be sufficient to protect the connection hardware for the required 1-hour fire resistance rating time. In fact, it would only provide 20 minutes of thermal separation time to the lower leg of the steel angle here. Whenever multiple layers of protection are used, the FDS states that 0.85 or 0.5 factor for determining thermal separation is only applicable to the layer that is directly adjacent to the connection itself. This is true regardless of whether this thermal separation is being provided by wood protection or by gypsum or by a combination of both of these. So in this example, which is similar to the previous one except that 2 layers of gypsum board are used instead of just a single one on the ceiling, the 0.5 factor would only be applied to one of these layers. It would be applied to the one directly adjacent to the protected element. In other words, since we apply that 0.5 factor only to the layer of gypsum that's directly adjacent to the protected element, in this case being the lower leg of that angle, the other layer of gypsum would not have to be multiplied by 0.5. And so we wind up with 40 minutes of protection from the face layer and 20 minutes of protection of thermal separation, that is, from the layer directly adjacent to the protected element, thereby adding up, of course, in this example to 60 minutes, which would meet the required fire resistance or thermal separation time in this particular example. So this would be an acceptable design here for protecting that connection. The FDS also provides guidance on detailing wood members and protection to account for char penetration. Where the edges of wood members abut, such as at the edge of a beam and column interface, the potential effects of char penetration should be evaluated. Let's define what we mean by char penetration here. So in order to grasp the concept of char penetration, we have to understand what char depth is first. Char depth is the distance between the location of the original wood surface prior to fire exposure and the location of the char front. And by the way, the char front is defined as the furthest extent of charring into the wood. So that would be the interface between the gray and the tan zone on this detail here, this diagram. As wood chars, its volume decreases, so the thickness of the char layer is actually less than the char depth itself. And this difference between char depth and char thickness is approximately 0.3 times the char depth at any given time. And that's the distance between this dotted line here and the interface between the white area and the gray area here on this diagram. That's approximately 0.3 times HR being the char depth. This phenomenon can result in the formation of a wedge-shaped gap which propagates along the interface between two wood members. FDS provisions indicate that ignition extends into these gaps a distance that is approximately twice the char depth. As a result, additional wood cover or blocking is required to protect the area around abutting edges. Fasteners used to attach protection are not required to be protected. This diagram depicts the profile of the char front in a floor-to-wall ledger connection when the steel angle hardware is properly protected. The char depth is labeled as A sub char, and the char thickness is the width of the gray area, as I mentioned. And you can see that the char front has formed a wedge-shaped gap at the interface between the wall and the 2x protection members. But the protection has been designed to account for char penetration at the interface between the CLT and the 2x protection members. So because of this, the char front does not quite penetrate all the way to the steel hardware, and so this would be considered an acceptable design because the hardware is not exposed at any point during this design period, during the fire resistance rating time. And you can see this is the wedge-shaped gap which occurs at the interface between this protection applied here, these 2x protection members, and the CLT on the CLT wall. If this collar had not been applied, or these protection members, these 2x protection members, obviously the steel angle ledger would have been exposed, and that would not be an acceptable design. Well, that concludes my presentation, but I wanted to point out that the FDS is available for free access on the AWC website at the web address provided here, and that's awc.org/resource hub. The FDS can be downloaded or can be accessed for free at that location, along with other AWC resources and design standards. So thank you very much for joining me, and I'll be happy to answer any questions that you may have at this time. Thanks.